it is my pleasure and privilege in uh, interacting with you over this period of time. Uh, Actually, I would like to spend just a minute to let you know that this course was first conceived when Professor Somnath Sengupta, who is there no more, he called me and said that why don't you plan a course on fluid mechanics. It was basically his initiative that has led to this uh, planning, and today I am feeling really very sad that he is not there with us uh, just to see that this course is taking its shape. We will basically try not to fully cover the book materials which are there over this coordinators workshop, because all of you are very experienced teachers, and there is no need that we go page by page for a particular course. Rather, we will be discussing about various issues that are important, not just for our own understanding, but for transmitting our understanding to our students who are newcomers to the subject. With this little bit of introduction, I would like to go ahead with the introductory concepts of fluid mechanics, and the topics that I will cover in this particular introductory lecture will be the following. First, the concept of forces acting on a fluid and concept of stress. This is the first concept that we will discuss. Second concept is viscosity, and third concept is surface tension. So we will discuss about these three concepts before Professor Som again takes over and discusses on compressibility issues. So what we will do first is to consider forces acting on a fluid. For a fluid, forces are important because a fluid may be at rest, it may be undergoing continuous deformation with certain characteristics depending on what are the forces acting on it. In continuum mechanics, which is the building block of the premises of the fluid dynamics that we study in the undergraduate level, in continuum mechanics we talk about basically two types of forces. The first type of force is called as body force. So what is a body force? A body force is a force that acts over a volume of a body. For example, gravity is a body force. So a force that acts over the volume of a body. And surface force a force that acts over a surface. Now, because the deformation of a fluid is strongly related to surface forces, and even a fluid which is not deforming also, a fluid under rest, that is also strongly governed by surface force, which is manifested in terms of pressure, which is force per unit area. Therefore, surface forces are very important in fluid dynamics, and we will try to get a thorough understanding of how to formally represent surface forces. So to do that, let us consider that there is a volume of fluid which is enveloped with a surface area, and let us take a small chunk from that fluid and in that small chunk we consider a small area. Let us say this area is dA. Now if we take out a small chunk out of the fluid, then what happens is that the remaining part of the fluid, we can represent the force exerted by the remaining part of the fluid on this chunk. It is like a free body diagram. If we isolate one part from a body, then we can represent the forces exerted by the other part on that part. So similarly, here we can isolate the force, let us say dF is the force which is acting on this part. So if these are differentially small, we can call these areas dA and dF, but if these are reasonably small, and we can use alternative symbols as delta F and delta A. But we are not going into the details of this intricacy of symbols. It is more important for us to learn the concept. So if we can find out the force per unit area on this small area, that is nothing but this is defined as the traction. Remember that this force dF, this force is a vector. Now the question is, this traction, this what we are calling as traction vector, this has a certain direction, so this is like a vector, but it is something which is more general than a vector. Why it is more general than a vector? Because let us try to investigate this. We have taken the area dA in a manner which is this one, which is drawn in this diagram. Now if we change the orientation of dA, if we make our dA like this, then the entire ratio of dF dA will change. That means that this traction vector not only depends on the area dA, but also depends on the orientation of the area dA. So if we take let me draw a separate figure. Let us say this is a point at which we are calculating the traction vector. Now you can choose the dA like this, you can choose the dA like this. I am just magnifying it, dA cannot be as large as what I am drawing, this is just a magnification of what is going on. So what we can see is that this traction vector will strongly depend on what is the orientation of this dA. How is this orientation of dA specified? The orientation of this dA is specified by its direction normal. So in that sense, area is like a vector. So area vector, the so called area vector, by that what we mean is that, let us say we have a area with a magnitude of dA. If this vector has, if this area has a normal direction which is shown by the arrow in this diagram, then, and if let us say eta cap is the unit vector in the direction of this normal, then the area vector is often represented by dA with eta cap, where eta cap is the unit vector in the direction of normal. So no matter how it is represented, it is important for us to understand that the traction vector, when it is represented, let us say we are representing the traction vector T, it will depend on the choice of orientation of the area. Because it will depend on the choice of orientation of the area, we give it a superscript eta. The superscript eta to indicate that the value of the traction vector will depend on the choice of orientation of the area. It is also a vector because, like a vector, it has its own components. So its x component is given by this subscript I for x component will become I equal to 1, this is x, I equal to 2 will mean y, and I equal to 3 means z. So it is possible that by a single index we can describe the component of a vector. The index equal to 1 means x component, index equal to 2 means y component, and index equal to 3 means z component. Therefore, we can see that to represent the traction vector we may require two indices. One is the index I to denote its own vector nature, another is a superscript eta that indicates the direction normal of the area on the basis of which we are calculating the traction. So traction vector in a loose sense is a vector, but in a more strict sense it is much more involved than a vector. To represent it more formally, we will go to the next diagram when we will consider some special surfaces. So some special surfaces are like this. Let us say that we consider a rectangular box. So this has its own, say this is a chunk of a fluid. In the previous discussion we were discussing about an arbitrary chunk of a fluid which is having an arbitrary orientation of its bounding surfaces. Now we have taken out a special chunk of a fluid which is a rectangular chunk of a fluid. The special characteristics of this rectangular chunk of fluid is that it has its faces, there are 6 faces of this rectangular chunk of fluid, and it has its faces either perpendicular to x or perpendicular to y or perpendicular to z. So these are special surfaces, and because these are special surfaces there are special notations to represent the traction on these surfaces. That notation is given by this very important consideration which is tau ij. So as we have discussed that there are two indices to specify the traction, and these two indices here are I and j. So what is the meaning of this I and meaning of this j? The meaning of this I is that it represents the direction normal of the surface. I will give you example which will help you to understand what do I mean, but let me complete the notation first. And j is the direction of action of the force. Remember this tau ij, this is like force per unit area. Now to represent this concept in the diagram, let us take one surface like this. Let us say we are considering this surface. So as we know that when you are considering a surface force, there are again two types of surface forces. One is a normal component of the surface force, another is the tangential component of the surface force, which we also call as shear component. So the normal component of the surface force per unit area, say this is the normal component. This normal component, let us try to write by the tau ij notation. So what will be I? I is the direction normal to the surface. This surface which is hatched by green color, what is the direction normal to this? The direction normal to this is x axis, right? For x axis we use alternative notations. X is x1, y is x2 and z is x3. So the first index is tau 1 for x1, and the second index is the direction of action of the force. What is the direction in which this force is acting? That is also acting in the x1 direction. So this becomes tau 1. In different books, different notations are followed. So in place of this, certain books will write tau xx, all the same. Some books will write sigma xx to represent the normal stress. Sigma is also used, and some books will just write sigma x, because there are two indices, they are not repeating and they are writing sigma x. So all these are equivalent alternative notations, and you can follow one of them provided you are following it consistently through the lecture that you are providing to your students. Then let us come to the tangential components. So this is a tangential component. So let us try to write its, what will be the first index? The first index will be 1, because still we are considering the green hatch surface whose normal direction is 1. And what is the second index? The second index is 2, because this force is acting on x2 direction. So the alternative notations, let us write, in place of this you could write tau xy, 1 for x and 2 for y. These are the really two, very standard notations for representing the same thing. Let us complete by showing the third component. So we can very quickly figure out what is this. Tau 1,3 or tau xz, right? Now to understand the convention, of course there are 6 surfaces. We will do it for another surface, and for the remaining 4 surfaces I will leave it on you as an exercise to complete. For this surface, which is just the opposite face, I want to show you how the symbols are written, because we want to adopt to a particular sign convention. What is that sign convention? The sign convention is, see here also you can see the similarity between this surface and this surface. The similarity is that both have normal in the x direction loosely, but actually their normals are oppositely oriented. For this surface the normal is along the positive x direction. For this surface the outward normal, by normal always remember, by normal of a surface we are meaning outward normal of a surface. So this, its outward normal is along the positive x direction. Here outward normal is along the negative x direction. So there is a particular sign convention which we adopt for this. What is the sign convention? The sign convention is like this. So if you are considering the normal stress on this surface, it will be, as per sign convention, negative will be along the negative x axis if the direction normal itself is along the negative x axis. Okay. So positive tau 11 for this surface, because it has already a normal in the negative x axis, positive tau 11 will be along the negative x axis. This is the sign convention. Similarly, positive tau 12 will be along the negative y axis, because the normal of the surface is along the negative x axis. And similarly, positive tau 13 will be along the negative z axis, because the normal of the surface is along the negative x axis. So this is the sign convention that we commonly follow. Other surfaces, I believe you will be able to handle very easily based on this discussion. Now, to complete this brief discussion on this representation of forces, so the question remains, what are these tau ij's? So we call these as in terms of a jargon which is difficult to absorb for young undergraduate students. These are called as components of stress tensor. It is very difficult to introduce in the beginners level that what do we actually mean by this, but we can simplify the conceptual understanding to a level which is acceptable to young undergraduate students. Otherwise, once you tell the name of tensor, it only creates tension in the mind of people. So it is better to talk in terms of that. So first of all, we understand that it is not really a vector. That much we understand. Otherwise, we could have told components of stress vector. We are not telling that. So it is something which is more general than a vector. In terms of representation, a vector will require how many indices for its specification? A vector will require one index for its specification. For example, if you have a force F, you can represent it by index I. I equal to 1 means x component, I equal to 2 means y component, I equal to 3 means z component. So that is what you could do for a vector. But because this is something which is not strictly speaking a vector, and the origin of that comes from the fact that it is a force per unit area where the result depends on the orientation of the area. So it requires two indices for its specification. So because of this, it is called as a second order tensor. So I mean, this is not a formal definition of a tensor, but this is a working way to relate your experience with the quantity. Like the number of indices required to specify will designate it as the tensor of that order. So like for example, a scalar doesn't require any index for its specification. So it is a 0th order tensor. Vector requires one index for its specification. So it's a first order tensor. Stress here requires two indices for its specification. So it is a second order tensor. So in that way, we can, I mean, there are more classical and mathematical definitions that of a tensor that I could provide, but it is not of importance to the audience that we are generally addressing at this level. So it is important for us to just let the students recognize that it is a force per unit area, but the beauty of representation of this force is that it also depends on the orientation of the area. So it requires two indices for its specification. To that extent, I think it is good enough to represent the stress. Now there are issues, we have understood that there are normal stress, normal component of stress and tangential component of stress, and these stresses are important when the fluid is at rest and even when the fluid is deforming. So if the fluid is subjected to a tangential stress, a fluid will be deforming no matter how small the stress is. But if the fluid is subjected to a purely normal stress, then the fluid will be under rest, and that is a state of hydrostatic stress, and that will be covered by Professor Sandipan Ghosh Maulik in his lecture. So I am not bringing that out in this in the purview of this particular discussion. The next concept that we will be discussing is viscosity. The prelude to this discussion is the continuously deformable nature of fluid, which was discussed in the previous lecture, and I will straight away come into the concept of viscosity with one very classical example in fluid mechanics. So the next item agenda is concept of viscosity. Let us say that there is a solid boundary which is a flat plate. So this is the leading edge of the plate. Classically, this is how we draw or we represent a flat plate like this. Let us say that fluid is coming from far stream with velocity, with a uniform velocity u infinity. Now let us try to understand that what happens to the fluid when the fluid comes in contact with the solid boundary. The fluid which comes directly in contact with the solid boundary feels the effect of the wall, and once it feels the effect of the wall, it tries to exchange its momentum with the wall, right? So for example, if two of us are walking and we are colliding, knowingly or unknowingly we are exchanging our momentum. So the fluid which is in direct contact with the solid boundary is exchanging the momentum with the solid boundary. When this exchange of momentum is complete, then we can say that the state of velocity of the fluid is same as the state of velocity of the solid, and that means that there is no relative tangential velocity between the fluid and the solid, which in a loose sense is known as the no slip boundary condition. Now let us assume that the no slip boundary condition is valid. Professor Som has discussed several examples by which he pointed out that the no slip boundary condition may not be valid under certain cases, and there are still controversies associated with that. I will not go into the details of those in the scope of this lecture, because in the undergraduate level when we teach fluid mechanics, we take the no slip boundary condition as the more common example rather than the slip based boundary condition, which is a more advanced example. So we will consider the no slip boundary condition and get ahead with the description of concept of viscosity through by accepting that as a condition at the boundary. So let us say that the fluid which is here at the interface between the solid boundary, that is the first layer of fluid, that fluid will be at the velocity of the plate. Because the plate is stationary, the fluid is also stationary. Now the second layer of fluid, let us consider a second layer of fluid. So this fluid velocity is 0. So let us try to draw consider a section and try to draw the velocity across this section. So velocity here is 0. Now let us come to another point here. What is the velocity here? The velocity here is definitely not 0 because it is not in direct contact with the wall, but the velocity here is also not u infinity. The velocity here is not u infinity because this fluid implicitly feels the effect of the wall. It does not feel it explicitly by being in contact with the wall, but it seems that there is a messenger in the fluid which gives the message to this layer of fluid that yes, there is a wall and you should be slowed down because of the presence of this wall. This messenger is nothing but the viscosity of the fluid. So what we can say is that here you can draw a velocity vector where the velocity is less than u infinity. Then if you go little bit further up, you will get little bit higher velocity because this is further away from the wall, so it will feel the effect of the wall less. In this way, if you go to a distance, you may figure out that at a certain distance you will reach almost a velocity of u infinity. Maybe for practical engineering purposes 99% of u infinity is as good as u infinity. So beyond this there will be no further change, no further appreciable change in velocity. So we can say that there is a region within which the effects of the wall are getting felt. This region can be very thin and this region can be very thick. It all depends on the Reynolds number, which will be discussed later on. But the objective to understand here is that you will get a velocity profile. The velocity profile is nothing but if you join the tips of the velocity vectors, and this velocity profile will indicate that there is a region where the effects of the wall are strongly felt, there is a region outside which the effects of the wall are not strongly felt. To continue with this discussion, let us consider a section which is further downstream. So the velocity here is 0 because of no slip boundary condition. Let us consider the corresponding level here. So here whatever was the velocity, here the velocity will be greater than that or less than that. We expect that velocity to be less than this one because now more and more fluid is under the influence of the wall. So you have velocity less, that means it will take more distance here to reach the u infinity level. So this is like 99% of u infinity. Here it will take more distance from the wall to reach this 99% of u infinity. Let us say this is the distance, this is the distance from the wall where it reaches 99% of u infinity. So we can clearly see that we are getting two demarcative regions. One region within which the effect of the wall is strongly felt, and that region can be conceptually visualized by drawing the locus of these points of 99% of u infinity. So this is an imaginary line, this black line, it does not exist in the fluid. This black line is an imaginary line and it demarcates the flow region into two parts. The lower region is where viscous effects are important. Remember that viscosity, the fluid has viscosity everywhere. It is just where viscous effects are important and where viscous effects are not important. So viscous effects are important. And here viscous effects are not important. So the region where viscous effects are important is also known as the boundary layer. And this black line is known as the edge of the boundary layer. Again, this is just an introductory lecture, so I want to give you the very basic concept of boundary layer without going into any mathematics, and the details of boundary layer theory will be discussed by Professor Ghosh Maulik towards the end of this coordinators workshop. Now, what we do with this? Basically, what we can clearly see, so let us complete the velocity profile here to finish this diagram. So, what we can clearly see here is that the region where velocity gradients are there, the viscous effects are strongly felt. How are these viscous effects manifested? These are felt in terms of the shear stress. So, we want to relate the shear stress with the deformation that the fluid is considering a time interval of delta t which is small, tan of delta theta may be approximated as delta theta. So that we are considering in the limit as delta t tends to 0. So if you do that, then the remaining algebra is very straightforward. So you can write limit as delta t tends to 0, delta theta by delta t is equal to delta u by delta y. And this is also taken in the limit as delta y tends to 0, because we are considering basically fluid layers which are just adjacent to each other. So this becomes, what is this? This is the rate of angular deformation or theta dot, and this is expressed as limit as delta y tends to 0 which is rate of change of partial rate of change of u with respect to y. Remember that this is not a complete description of theta dot, because here we have assumed that there is only one component of velocity which is u, but in general the flow field may have multiple components of velocity, x component which is called as u, y component which is called as v, and z component which is called as w. But here we can conceptually say that this is just to indicate that if you have one component of velocity, how can the rate of deformation, rate of angular deformation be expressed in terms of the gradient of that velocity. So now we have the rate of deformation expressed in terms of the gradient of velocity. On the other hand, you have the shear stress which is tau. I am not in particular giving the notation tau with the subscripts, but let us work with the subscripts so that we relate our previous discussion with this one. So this is the solid boundary and this is the fluid element. So if we are interested to represent, let us say this is x axis and this is y axis. If we are interested to represent the shear stress on this, what will be the indices? What is the first index? What is the direction normal to this? The direction normal to this is y. So tau 2, and the direction of action of this is x or 1. So tau 2 1 or tau yx. So we can write that tau yx, or simply just tau, because this is the only tau that is there in this particular two-dimensional system. So tau is related to, it is a function of theta dot, that much we can say. We are relating a cause with an effect. This is what is called as constitutive behavior. That is, we are expressing the shear stress with the rate of angular deformation. Now what is this functional dependence? The functional dependence depends on what is the type of fluid. So for different types of fluids, the functional dependence may be linear, non-linear, whatever. So we can say that there are certain types of fluid for which this functional dependence is linear, and that type of fluid is called as Newtonian fluid. For a Newtonian fluid, the functional dependence is linear. That means tau is a linear function of theta dot, and in fact it is linearly proportional to theta dot. So the constant of proportionality this mu is known as viscosity of the fluid. Okay. So first of all, viscosity of a fluid is defined only for Newtonian fluid. For fluids which do not obey the Newton's law of viscosity, this is known as Newton's law of viscosity. The fluid which doesn't obey the Newton's law of viscosity, we cannot define viscosity, we can only define something which is a parameter which is viscosity like, that is called as apparent viscosity, but that is not the true viscosity. So you can find out the dimension of viscosity. I am not going into the details of that because these are very straightforward. You can divide the dimension of tau with the dimension of theta dot, and you will get m L to the power minus 1 T to the power minus 1. So that is the dimension of viscosity. I am not going into all those trivial things, but let us conclude the discussion on viscosity with a very important concept that is called as kinematic viscosity. Of course, the other concept that we will discuss related to viscosity is that what is the origin of viscosity in brief physical sense. So kinematic viscosity, it is defined as viscosity by density and often symbolized by nu. Question is, why is this parameter important? Now you can, first of all, you can figure out that if you work out the dimensions of this is meter square per second. So this, the unit of this in SI system is meter square per second. So this doesn't involve any parameter which is related to mass. There is no kg involved. So it's a totally kinematic parameter, but that's not all. We have to understand that what is the physical implication of this. So let me tell you a related issue, but not from the concept of fluid mechanics to explain this. Very often I see that there are many strict teachers in different institutes. I mean, IIT is of no exception, so there are many teachers who are very strict. So the strict teachers, what they do is that even in the morning 7:30 there is any class, the strict teachers will not allow students beyond passing of a certain time, let us say 2 minutes, 3 minutes, 4 minutes. I have seen teachers standing outside the class in 7:30 in the morning, and just at dot 7:30 they will enter, and they will not allow many students to get into the class after say 7:35 or 7:40. So let us say that 7:35 has just come and the teacher is saying, I am not going to allow you beyond 5 minutes. Then there is a disturbance. This student who gets this message knows that he has a friend who is sleeping in the hostel and he is desperate to get an attendance because otherwise he will be deregistered from the course. So this student has to come. So this student sends an SMS or phone call by mobile phone to his friend who is sitting in the hostel. So this is a message of disturbance. The professor has created a lot of disturbance. So this message of disturbance is propagated here by mobile phone, in reality in fluid by viscosity. So that message is propagated. Now the student has its own inertia. The student is peacefully lying in the bed of the hostel. So he has his own inertia, he doesn't want to get up. But there is a message that he has to get up somehow. So the important thing is that how the student reacts considering his inertia. If his inertia is very deep, even if 10 missed calls have come, he will still lie down on the bed and he will not come to the class. But if the student's inertia is less, he will quickly jump out of the bed, just somehow brush their teeth and come to the class within 5 minutes by cycle. So here you see this mu is like the ability of the fluid to accept the disturbance. So this is the messenger of disturbance. This is the tendency of the fluid to sustain its motion. Rho is related to the mass, and mass is the measure of inertia. So this rho tells the fluid that let me retain my momentum, and this mu is related to the disturbance of momentum. So it is the relative ability to accept the disturbance of momentum with respect to its tendency to sustain its momentum, and that is therefore more important than the quantity viscosity itself conceptually, and that is what is known as kinematic viscosity. The final remarks on viscosity, that what are the parameters on which the viscosity depend? Well, there are several parameters on which it could depend, but to understand that, let us briefly discuss about the origin of viscosity. So there are the origin of viscosity, it depends on what type of fluid you are addressing. Is it a liquid or a gas? For a liquid, the viscosity is strongly related to intermolecular force of attraction. For gas, however, intermolecular force of attraction is not very dominating. All of us know that gases have much less intermolecular force of attraction than liquid. So for gas, the more important mechanism for having viscosity is transfer of molecular momentum. So what is transfer of molecular momentum? I will just briefly discuss. Let us say that these are slow moving molecules, and let us say these are fast moving molecules. These molecules are vibrating with respect to their mean position, and they are having all sorts of motion, translation, maybe rotation also. So in this way, when a slow moving molecule joins the layer of the fast moving molecule, what it does? It tries to slow it down, slow the fast moving layer. On the other hand, if the fast moving layer of molecules joins the layer of slow moving molecules, what it does? It tries to enhance the speed. That means the exchange of molecular momentum is trying to create a disturbance in momentum. Okay, so this is the mechanism in which the viscosity works in gases. Now, based on this, let us try to answer a question. If we increase the temperature for normal cases, except for exceptional cases, for normal cases, what we expect? If we increase the temperature, will the viscosity of a liquid increase or decrease? It will decrease, because if you increase the temperature, what will happen? If you increase the temperature, the molecules will have more thermal energy to overcome intermolecular forces of attraction. But if you increase the temperature, so this mu will be less. But if you increase the temperature, what will happen? There will be more vigorous transfer of molecular momentum between layers, and that will increase the viscosity of the gas. Okay, so we can see that based on the mechanism we can figure out that what is the effect of temperature. Effect of pressure on viscosity is not that severe as that of temperature, so we will not bring that in purview here. Now the final concept that I will be discussing, I will not be discussing in details because of the interest of time, that is the surface tension. And in surface tension, the surface tension is a very neglected concept in teaching fluid mechanics. In the undergraduate fluid mechanics curriculum, all books will have some discussion on surface tension, but all teachers will knowingly or unknowingly try to avoid it. And I do not know why, but surface tension is a very important conceptual understanding in fluid mechanics. So I will give you first a brief conceptual understanding, and then I will discuss about the derivation of a formula, and the application of that formula for solving some problems will be covered in the tutorial of this course. So let us say,
So we are now discussing about surface tension. Let us say that there is a beaker. In the beaker, there is a surface. I have drawn it like flat, it need not be flat. I mean, this is the problem with many of us as teachers. When we want to draw something curved, it becomes straight. When we want to draw something straight, it becomes curved. So, this I have not intentionally tried to draw as curved or straight, I have just kept it as it is. Now, let us say that there is a molecule, this is the liquid, and there is a gas. Let us say there is a molecule here. If there is a molecule here, it will be attracted equally by liquid molecules all around. But let us consider some special molecules. Let us consider that there are some molecules at the interface. If there are some molecules at the interface, then these molecules are very peculiar. From the bottom, liquid is trying to attract it. From the top, gas is trying to attract it. Which attraction is more severe? Liquid attraction is more severe because liquid is more densely packed. So based on that, these green molecules would have a tendency to get dissolved into the liquid. But in reality, they don't get dissolved into the liquid because to stay at the interface, they possess some additional energy by virtue of which they can sustain this imbalance and still be there at the interface. That energy is known as surface energy, and because of the special force at the interface, these molecules are in the state of some kind of tension. This force per unit length is also known as surface tension. So this is a very basic paradigm. Now the question is that if you have a curved interface, because of the surface tension, there is a difference in pressure across the two sides of the interface. First, we will develop the concept that in which side the pressure will be more and in which side the pressure will be less. This is the first thing, and the second thing is what is the quantification of this pressure difference. To do that, let us say that this is a portion of a curved fluid element. So the surface tension acts in this way, tangentially. So this surface tension force will have a downward component. This surface tension force, let us call it FST, surface tension force, will have a downward component. Let us say the pressure on this side is P1 and the pressure on this side is P2. This is P1 into some area and this is P2 into some area. So the green element is in equilibrium under the action of the force due to P1, P2 and surface tension. So we can write P1A plus force due to surface tension is equal to P2A. So you can clearly see that P2 minus P1 into A is balanced by the force due to surface tension. So because of the surface tension, you have a pressure difference across the two sides of an interface. And in the next slide, I will try to briefly show you a derivation on how to calculate this pressure difference in terms of the surface tension. So let us try to follow this slide. Let us say that you have a surface. This is the surface that I am talking about, this surface, with curved surface with sides x and y. Okay. So this is like a curved rectangle. So its area is x into y. Now let us say there is a stretching of this surface, so it occupies a new configuration. which becomes x plus delta x becomes x plus delta x, and y becomes y plus delta y. So there is we have just now conceptually understood that this curvature of the interface implicitly means there is a pressure difference across the two sides. So across the convex and the concave side. So let if delta P be the pressure difference, then if A be the surface area, A is nothing but x into y, and let us say that delta Z is the displacement along the normal direction, then the work done by the pressure in virtual displacement is the delta P into A into delta Z. Delta P into A is the force times delta Z is the work done. Now this work done is related to the change of surface energy. Where is this work being spent? This work is being spent to create a new surface, because x into y has now become x plus delta x into y plus delta y. So some additional surface has been created. That surface must sustain with the help of some energy. That energy has come from this work done due to stretching of the surface. So you can say that the work done due to this force is delta P into, so it is written here, delta P into x y into delta Z. This is basically delta P into A into delta Z, and this work is related to the surface energy. This x into delta y plus y into delta x is the additional area that has been created. That times sigma, sigma is the surface tension coefficient. So that times sigma is the surface energy. So if you equate the work and the energy and you use some very simple similarity in geometry, so for geometry we require these two important understandings: the radius of curvature of the surfaces. So the surface, this is the one principal curve of the surface, this has the radius of curvature R1. This is another principal curve of the surface, this has radius of curvature R2. So these are the radii of curvature called as R1 and R2, and this R1 and R2 are related to x, y and z by the similarity relationship. R1 by R1 plus delta z is nothing but x by x plus delta x. From this is like similar triangle. So R1 is related to x and delta z by this relationship. Similarly R2 is related to y and delta z by this relationship, and these relationships can be substituted in this work energy expression to give this very important final expression. Delta P is equal to sigma into 1 by R1 plus 1 by R2. So this is the pressure difference across the two surfaces because of the surface tension. And in the tutorial section of this particular lecture, problems will be solved related to this particular use of this particular formula. Remember the special case of a spherical droplet. A sphere has a uniform radius of curvature. So for a sphere, R1 equal to R2 equal to R. Therefore you can substitute R1 equal to R2 equal to R, so that becomes delta P equal to 2 sigma by R. So for a spherical surface, this delta P equal to 2 sigma by R. So to summarize, in this introduction I have discussed about three concepts. One is the concept of forces acting on a fluid in terms of body force and surface force, and the surface forces expressed in terms of stress tensor components. That is the first thing. The second thing is the concept of viscosity, and the third thing is the concept of surface tension. And this particular lecture will be concluded by Professor Shom, who will discuss about one very important concept related to properties of fluid, that is the compressibility of the fluid. So I will hand it over to Professor Shom.